Jevons paradox and the limits of interstellar travel. Summary statement. What appears to be a hard limit, whether in resource use or space travel, is often a constraint of the current input system, not the desired outcome. Efficiency expands demand until bottlenecks force a shift to new inputs, unlocking entirely new possibilities beyond perceived limits. Section 1, Introduction, The Illusion of Limits. Every era believes it has discovered a boundary, a ceiling, a point beyond which progress either slows or collapses. In the 19th century, it was coal. Today, it may be compute, energy, or even the feasibility of interstellar travel. At first glance, these limits feel real, grounded in physics, economics, or material scarcity. But history has a habit of exposing them as something else entirely, not true limits, but constraints within a particular system. This is where Jevons' paradox enters the frame. Often misunderstood as a warning about overconsumption, it actually reveals something deeper and more unsettling. The paradox is not just about resources. It is about perception, specifically our tendency to confuse inputs with outcomes and constraints with final boundaries. Section 2. Defining Jevons' paradox clearly. Jevons' paradox states that as technology improves the efficiency of using a resource, the total consumption of that resource tends to increase rather than decrease. William Stanley Jevons observed this in 1865 with coal. As steam engines became more efficient, coal usage did not fall, it surged. Efficiency made coal cheaper to use, which expanded its applications across the economy. At first glance, this appears paradoxical. Should not using less coal per machine reduce total consumption? Under standard economic thinking, lower costs increase demand that is normal. The paradox emerges because people expected efficiency to act as a conservation mechanism. Instead, it acted as a catalyst for expansion. But even this framing is incomplete. It still assumes the resource itself is the central variable. And that is where the real confusion begins. Section 3. The core misinterpretation. Input versus output. The critical mistake in interpreting Jevons' paradox is focusing on the input rather than the output. Inputs are resources, coal, oil, compute cycles, memory. Outputs are what we actually want: heat, mobility, intelligence, productivity. No one desires coal for its own sake. Coal is valuable because it produces heat and power. Similarly, we do not want compute. We want what compute enables: AI systems, automation, insight. Efficiency reduces the cost of the input per unit of output. But as output becomes cheaper, demand for that output expands. From the input perspective, this looks like overconsumption. From the output perspective, it is simply expanded access to value. The paradox exists only if you measure the wrong thing. Section 4. The three-layer mechanism. To fully resolve the paradox, we can break the system into three interacting layers. Type 1, efficiency, local optimization. We reduce the amount of input required per unit of output. Engines burn less fuel per mile. Models use less memory per computation. Type 2, rebound, demand expansion. Lower costs, increase usage. People drive more. AI applications proliferate. Total input consumption rises. Type 3, substitution, system upgrade. Eventually, the system evolves. New inputs replace old ones. Coal gives way to oil, then nuclear, then renewables. The bottleneck dissolves at a higher level. Jevons' paradox primarily describes the tension between Type 1 and Type 2, but the full story only emerges when Type 3 is included. This content is brought to you by Bobby Giggs. Promote your brand here and reach a wide audience across platforms like YouTube, Instagram, and Facebook. Follow the links in the description to get started. Section 5. Historical Case Study. Coal to Modern Energy. Jevons feared that Britain would run out of coal. His concern was logical. Coal-powered industry and rising demand suggested eventual scarcity. In the short term, he was right. Efficiency drove coal consumption higher. But over the longer arc, the system did not collapse under coal scarcity. It evolved. Oil offered higher energy density. Natural gas improved distribution. Nuclear unlocked entirely new energy scales. Solar and renewables further diversified the input base. We did not save coal. We transcended it. The desired output, energy, continued to expand. The input simply changed form. Section 6. The bottleneck framework. What Jevons identified as a paradox is better understood as a bottleneck signal. A bottleneck occurs when a system's growth is constrained by a specific input. Efficiency temporarily relieves pressure, but often accelerates growth, which intensifies the bottleneck. This pressure is not a failure, it is a trigger. It forces the system to search for alternatives, to innovate, to substitute. In this sense, bottlenecks are not endpoints, they are transition points. Section 7, Extending the Model, Interstellar Travel Constraints. Now consider the modern claim interstellar travel is impossible. The arguments are familiar. Energy requirements grow exponentially. Rockets are inefficient. Radiation is lethal. Materials cannot withstand the journey. These are real constraints, but they are all framed at the level of current inputs: chemical propulsion, fusion limits, shielding materials. This is the same category error. We are treating the current input stack as if it defines the boundary of the outcome, but the desired output is not better rockets. It is interstellar access. Section 8, the system-level perspective. History shows that we rarely solve problems by optimizing the existing input indefinitely. We solve them by changing the system. Flight was not achieved by perfecting horse-drawn carriages. Electric lighting did not emerge from better candles. Digital computation did not evolve from mechanical gears alone. Each breakthrough involved a shift in the underlying input paradigm. The same principle applies here. What appears impossible within one system often becomes trivial within another. Section 9. The threshold effect. Efficiency plays a crucial role in this transition. By lowering costs and expanding usage, efficiency pushes systems toward critical thresholds. These thresholds expose the limitations of the current input and create the conditions for a breakthrough. At that point, progress is no longer incremental, it becomes discontinuous. The system does not improve, it transforms. Section 10, Implications for the Future. This framework has immediate relevance. In artificial intelligence, more efficient models do not reduce demand for compute, they expand it. This drives new applications, which in turn stress existing hardware and energy systems. The result is not collapse, but transition. New chip architectures, alternative energy sources, distributed compute paradigms. The same pattern will apply across domains. Policy approaches that focus solely on conservation misunderstand the dynamic. Efficiency is not a brake, it is an accelerant. The real challenge is not limiting usage, but anticipating the next bottleneck and enabling the transition beyond it. Conclusion: beyond the paradox. Jevons' paradox is not a contradiction. It is a misinterpretation. The apparent paradox dissolves once we distinguish between inputs and outputs, and once we recognize that systems evolve. What looks like overconsumption is often expansion. What looks like a limit is often a bottleneck. And what appears impossible is often a problem waiting for a new system. We do not solve limits at the level of inputs. We solve them at the level of systems.